Hello, everyone, and welcome to today's webinar on satellite-based wetland mapping in Canada's Boreal region using OBIA. We are excited to welcome Rebecca Edwards and Michael Merchant from Ducks Unlimited, who will be talking about their organization and how they use Trimble's eCognition software out on the field. CANSOL is around to help organizations collect, analyze, design, and build more efficiently and profitably to help improve your workflow from field to finish. Trimble's eCognition is one of many softwares that CANSOL offers to our customers. Duck's team of analysts perform various image pre-processing tasks, extensive aerial field data collection campaigns, object-based image segmentation and classification with eCognition, and finally, image interpretation and manual editing. Now, before I hand the presentation over to Rebecca and Michael, please note that at the end of the webinar, there will be a quick Q&A session. And so if at any point there is a question you want answered, you can refer to the questions panel on the side of your screen. So without further ado, thank you everyone for joining us. And on behalf of the CANSOL team, I'd like to once again welcome Rebecca and Michael to our webinar.
Awesome, thank you very much. So again, my name is Rebecca Edwards, and I'm here with my colleague, Michael Merchant, to present satellite-based wetland mapping in Canada's Boreal region using object-based image analysis. So first, I'm going to start off by giving a presentation on the National Boreal Program, Introduction to Wetlands, Wetland Remote Sensing and Challenges, and lastly, Ducks Unlimited Canada Boreal Wetland Inventory. And then I'll hand it over to Michael, who will give you a hands-on demonstration using how we use eCognition for our wetland inventory. So what does the National Boreal Program do? Well, the Boreal Program has 20 years of experience working with government, Indigenous people, and industry to develop comprehensive science-based solution for conserving boreal wetlands. Specifically, our program handles boreal wetland policy, protected areas, and sustainable land use, and science, focusing on conservational activities that threaten waterfowl and their habitat. And wetland mapping is a part of these processes to help find solutions. So why are wetlands important? The boreal forests of Canada consist of a vast mosaic of forests, lakes, rivers, and wetlands that cover more than 1.3 million square kilometers of Canada. 85% of Canada's wetlands are located in the Boreal, providing critical ecosystem services such as water filtration and storage, carbon sequestration, and habitat, as well as traditional cultural practices. So now let's talk about what exactly is a wetland. So according to the Canadian Wetland Classification System, a wetland is where the water table is at, near, or above the surface of which saturated for a long enough period to promote such features as wet altered soils and wet tolerant vegetation. Now I've bolded two really important words here, which are saturated and vegetation. So hydrology and wetland vegetation are very key characteristics to determine wetland type. Now, as you can see here in the images below, there's quite a wide range of different wetland types. It ranges from different hydrology, where the hydrology can be sea pooling at the surface, or it can be more dry. You can also vary from being treed, shrubby, and graminoid. And it's also important to note that wetlands can also be dry and have poor nutrients, or can also be very green and rich in nutrients. So now I would just like to go over the 5 major wetland classes through the Canadian Wetland Classification System. So first is shallow open water. So this is where water depth is less than 2 meters, yet is too deep for emergent wetland plants to establish. Marsh is a mineral wetland soil with shallow organic deposits, often a transition between open water and shorelines. Fen are peatlands that receive water from a combination of precipitation, runoff, and groundwater, and are more nutrient availability. Whereas bogs are also peatlands, but they receive much of their water through precipitation and more nutrient poor compared to fens. And lastly, we have swamps, which are mineral wetlands less than 40 centimeters of peat and have hummocky terrains with pooling of water. So these are just the general characteristics of these wetlands, but these do vary. I like to tell a story that I once did field work in Grand Prairie recently in the summer, and we were in a tamarack swamp, which had water that went past my knees. So high precipitation event that caused a flooding of the swamp. So it's really interesting how water and hydrology fluctuate in swampy areas. So like I mentioned, wetland hydrology and wetland vegetation are very important when looking at wetland characteristics, especially when we talk about wetland mapping. So again, wetland hydrology is seasonal or permanently waterlogged, and it's water slightly below, at, or above the surface. Now, when we take this into account for wetland mapping, we can use sensors such as radar or synthetic aperture radar, SAR, to be able to identify more moist areas in your landscape. SAR has been widely used in the literature for wetland classification. Also, digital elevation models, DEMs, are widely used as well because we are able to denote where uplands are and where basins are, and that's where mostly water will reside for where wetlands are. Next is wetland vegetation. So this is where vegetation is adapted for life in saturated or flooded soil conditions. Species can be obligate or facultative. And obligate just means that a certain vegetation type will occur in that wetland type only, whereas facultative can be found in uplands and wetlands. Now, different vegetation types will show up as a different spectral signature in multispectral resolution. So it's really important to understand what vegetations occur in what wetland types to just have a better understanding when you're mapping the area. So now let's start looking at some multispectral imagery. So this is a Landsat scene from the Slave River Delta. And as you can see here, this is just a true color image. And it's kind of hard to determine the wetlands just by using a true color image, as you can probably denote from hydrology of where the wetlands reside. But if we change it into a false color composite using shortwave, near, and red bands, we really start to see the spectral signatures of the vegetation pop out. So then again, start to look at, again, the hydrology and the different vegetation types. So again, based on hydrology, we know that marshes will most likely reside in deltas or ringing water bodies, or even in the deltas of the river. We can see fens there in the lower bottom of the image, where it's kind of like a connecting flowing feature by two water bodies. And you can see swamps, again, are going to be located adjacent to water bodies as well. And something interesting to note as well for spectral signatures is the deciduous upland in the right corner shows this bright orange, whereas the coniferous or conifer uplands are showing a dark brown. It's also important to note that deciduous uplands and say the swamps could be a hardwood swamp or a shrubby swamp, will have similar spectral signatures. And that's where wetland mapping can be quite challenging. So what type of wetlands are in this image? What features are used to distinguish or delineate these wetland types? And is there a way to classify these wetlands within the region that is mutually exclusive? So now I'd kind of like to get into some of the challenges that occur when we would like to map wetlands in the Boreal. So here is an ecozone map of Canada. As you can tell, there are many different ecozones that range in temperature, precipitation, and climate. It's interesting to note that we do most of our work, or have done most of our work, in the Boreal Plains, where the wetlands are very large, very vast, and cover an extensive amount of area. But our last couple summers, we've been up north into the Taiga Plains and Taiga Shield. And specifically in the Taiga Shield, the wetlands are much smaller, is more barren lands. And so even just going across the country, you can tell there's lots of different variations in wetlands. We can also see that the Boreal contains the highest percentage of wetlands in Canada. The Boreal forest is outlined in red there. And then, like I mentioned before, going across each ecozone, we can see that there's a lot of different wetland types based on size and extent, complexity, and also just the amount of growth forms available across the country. So getting into some other challenges with remote sensing, or wetland remote sensing, is there can be a wide range of features within a single wetland class. So for example, some of our older classifications were using Landsat imagery, so a multispectral resolution, which is a 30-meter pixel resolution. And so in a 30-meter pixel, you can imagine we could capture marsh, open water, and maybe even fen surrounding the area. Whereas nowadays, in our most recent projects, we're using Sentinel-2 imagery, which is a 10-meter resolution. So again, that just goes to show that having a higher resolution in wetlands, we'd be able to identify smaller wetlands and have a more accurate classification. Another point is some upland areas will have the same spectral signature as wetland areas. And I mentioned that with the deciduous and swamp, but you can also see this here in this image. On the left, you can see the white popping out there, which is lichen, and that appears to be a bog, so a lichen bog. And on the right, as you can see, lichen as well, and this is more of a lichen upland. So this is really important to consider as a user when we are mapping wetlands, is that the algorithm or our supervised classification may pick up these spectral signatures and denote it as the same, whereas as a user, we would have to go in there manually after and make those changes that are needed. Also, delineation of wetland extent can be difficult. So again, this is with the size, but also mostly the gradation. So the wetlands transition between each form. So this is just an image here to show that we have a tree fen moving into a shrubby fen and a marsh. And these lines aren't very distinct, and they can change depending on tree sizes and shape. And lastly, for challenges, we look at water level changes over time. So here we have an image in 1988, and I'm going to scroll it all the way to 1995. And as you can see in each image, the wetland is drastically changing in terms of hydrology and also vegetation as well. So classification of wetland type can be dependent on an image capture date. And ideally, our wetland inventory should be refreshed over time. And this just depends on the funding availability. But of course, we know wetlands are changing drastically in our with climate change. So now I would like to get into DUC's wetland classification system. So at the top, we have our broad cover groups, which is wetlands and uplands, going down to our major soil groups, which is organic wetlands and mineral wetlands. And finally, our major wetland classes, of which I talked about before, which are bog, fen, swamp, marsh, and shallow open water. So this is based on the Canadian Wetland Inventory. So this was established in 2002 by Ducks Unlimited Canada, Environment Canada, the Canadian Space Agency, and North American Wetland Conservation Council. So the CWI is a national approach to establish consistent framework to map the wetlands. So we currently don't have an overall Canadian wetland inventory. So this approach allows people to combine forces to have the same framework to map and where we map in the Boreal. So I have the link to the website below, but if you go onto our National Boreal website, you can get to this map, which is our completed areas of the 5 wetland classification. As you can see here, our completed projects are in navy there, or in blue, and our in progress are in pink. And if you zoom into an area, a study area, so this is the Uticuma region, you are actually able to see our classification if you zoom in far enough. So if you're interested in seeing wetlands in your area and we have it completed, if you go to our website, you can see a more detailed version of this. And it's a very, very cool interactive tool. So next I would like to talk about our minor wetland classes. So this breaks down our 5 wetland classes more detailed into a 19-class classification system based on hydrology and vegetation. This is called our Enhanced Wetland Classification System, or EWC. So the EWC defines major and minor wetland classes for the entire ecozone. On our website, on the Boreal website, we actually have a field guide to wetlands of the Boreal Plains ecozone in Canada if you are interested. Our EWC is applicable for ground level surveys, but also designed for helicopter-based surveys as well. This is currently our up-to-date map of the completed EWC projects. So everything in yellow is our current completed projects. The one project there in pink is in progress. It's of the Wood Buffalo National Park. Our green projects there are our completed CWCS, so the Canadian Wetland Classification System. And then our blue projects there are the general earth cover classifications. So these are some of our old projects where the classification was more based on vegetation than it was wetland type specifically. And just to date, we have approximately over 216 million acres of EWC mapped to date. So now I'd like to spend a little bit of time talking about our methodologies of how we create the EWC or our CWCS classification. Michael, again, will go into a lot further detail and show you on eCognition specifically, but I thought I would go through it. So first we have our satellite imagery that we collect. Again, I've talked about our previous projects using LatinSat imagery, 30-meter resolution, freely available, cloud-free, and we also use Sentinel-2 imagery that again has been recently available free as well, and it's a 10-meter resolution product. Again, we look at this in cloud-free as well. And we select these satellite images based on a date between June and early September. So we're getting peak vegetation growth during this time. And so next we also will collect ancillary data. So this can, one, go into our classification in eCognition to help our algorithms and our supervised classification delineate wetlands. But we also use this data to help the user identify wetlands with their eye to train them before they enter the area for fieldwork. So our ancillary data can be our SAR imagery that we talked about. That's the picture on the left there. And again, for our SAR data, we have collected fall, spring, and summer data and stacked them together and mosaicked them. And this just helps us be able to identify wetlands with fluctuating, with a lot of seasonal fluctuation. That image on the right there in ancillary data is WorldView 2 imagery. So we also are very lucky to be able to use WorldView 2 imagery in our recent project in the Acacho in the Northwest Territories. It's one of our largest projects to date, and we couldn't in our fieldwork reach the entire study area. So having extra data in areas we couldn't go to was really important to train the user and the mapper to be able to map out wetlands that we weren't able to go to on the ground. Another type of ancillary data are like burn data sets, so vector data sets, or forest inventory, and this can help us mask out burn layers or even upland layers to help the process go much smoother. So we take all this imagery and we process it. We use certain software such as ERDAS, or we use Snap or Send2Core as well. And then we're going to plug it into eCognition and run our object-based image analysis. Again, Michael will go into more detail, but we use a segmentation approach and a supervised, more random forest approach when we go ahead and do this. So once we have a segmentation, we are able to use these objects as field sites for our fieldwork. So again, we are very lucky to go to these amazing places for fieldwork. So this summer we actually went to Dawson City, which was really cool, and this is where this image was taken. And that project, the fieldwork ranged a month, where some of our projects can be from a week to 2 weeks in the field. And so our fieldwork is helicopter based. And so we have 4 people in the helicopter. One's the pilot, the other person is the navigator, and the navigator has a GPS and uses the tablet to identify objects in the field and navigates the pilot to these objects. We have the vegetation caller, and the vegetation caller will call out vegetation types once we arrive at the site, heights and species to be able to give a detailed wetland call. And then we have the recorder in the helicopter as well that will record all this information down. And so in fieldwork, we collect detailed vegetation as well as lots of photos around the area. And this goes into giving us training data and validation data for our accuracy assessment. And once we finish our accuracy assessment, we have our final wetland classification. Now, lastly, I would just like to talk about, once the mapping is all finished, how we can use our wetland classification to make big decisions within our company. So while the EWC locates wetland types that exist, our inferred products focus on the underlying factors forming those wetlands. So this is just the satellite imagery, a Landsat satellite image in that false color composite. And here I'm going to overlay our classification, but also our inferred product. So for example, here's our wetland classification that helps us understand water flow and in turn can help us make informed decisions on forest roads, wetland crossings. So in green is a low risk or a stagnant water flow, whereas the red is a high risk where it floods often. And again, like I mentioned before, it just makes us to make informed decisions on foresters to make forest road crossings. And this is our operational guides for forest road wetland crossing if you're interested. And lastly, for a couple more inferred products. So again, this is based on hydrology and vegetation, but we have hydrodynamics, soil moisture, and nutrient regime. So again, all of these maps are used through our best management practices team and our science team to make very large decisions, which I think are very important. So great, so that's all for me. That's my presentation there. And I'm going to now pass it off to Michael, who's going to give you a demonstration with eCognition.
Thanks, Becky. Let me know when you send over the screen share. May presenter. Okay, are you able to see that, Becky?
Yes.
Good, good. Okay, yeah, thanks for that first part of the presentation today, Becky. That was great. Before we get in, I'm just going to quickly introduce myself again. So I'm the lead remote sensing specialist for the Boreal program of Wetlands in Canada. And I'm based out of Edmonton, Alberta, and I've been with the program for about 5 years now, completing various wetland mapping projects across Canada's Boreal region. And so today I will be demonstrating a working example of how we develop wetland classifications using eCognition developer software, and I'll be demonstrating using a large collection of remotely sensed data. So with that, I'm just going to get into it. And so for this example today, this will be a study site in the Taiga Plains ecozone of the Boreal Forest. And it's located in southern Northwest Territories, so just kind of above the Alberta border in Canada. And that's near the town of Fort Simpson, if anyone knows the region. And that's this bright feature here you can see in this optical Sentinel-2 image that I'm hovering over. And the region is characterized by discontinuous permafrost, and it's extremely wetland dominated, most of which are peatlands like Becky described, but also we have occurrences of forested uplands, either deciduous or coniferous in coverage. And these classes are all represented in my class hierarchy over here to the right, where we have our various upland classes and the wetland classes that I will be talking about today. So just, and I know Becky gave a good overview of these wetland classes, but just to skim over them quickly again, I'll be identifying open water classes, which are your, open to permanently flooded systems, but also can contain aquatic and floating vegetation. We have fens, which are a peatland type, vegetated, more connected to the groundwater system, so kind of moving water across the landscape. Bogs, another peatland type, but more poor, isolated, a little bit less diverse than fens. And then swamps in teal here, which are a difficult class to map, but they're kind of transitional from your bogs and fens. And hydrologically, they kind of have a fluctuating water table. And then just to note, there is very little marsh present in this study area, so I did omit that class from this demonstration today. However, there are many regions of the boreal forest and where there are extensive marsh coverage, so for example in delta regions. So those are the classes I'm going to be mapping in this demonstration here. And I'm going to get into now the Earth observation data sets that I've plugged into this project workflow. So the first one is Optical Sentinel-2, and that was acquired for the European Space Agency's Open Access Hub.
Hi, Michael. Sorry,
Yep.
apparently some people can't see your screen.
Huh. Okay. Let me try this. I went to the clean version. Maybe that works.
Because I can see your screen, but some people are seeing they can't see it.
Oh, interesting. People can see your screen. Click to stop sharing. I'm present. This is strange. I can see they can see it now, I think.
Okay, some people are saying they're good now. Okay, awesome.
Okay.
So you can keep going.
Okay, thanks for that. Yeah, just give me a
Yeah.
heads up if I miss any of those questions in the box there as well. Thanks,
Oh,
Becky.
no problem. Yeah.
Okay, where was I? So I was going over the different Earth observation data sets for this demonstration. And the first is that optical Sentinel-2 data. So that's a multi-band raster product that we see here with ranging pixel resolutions. But for our pre-processing, what we do is we run an algorithm called Sentu Core, and it converts the top of atmosphere to bottom of atmosphere reflectance values. And then we utilize any of the 10 and 20 meter band resolutions into the final process product, which you see here. And I am just showing a true color composite here of the data, but I will show that that band combination that Becky was talking about earlier to highlight kind of the various land cover types across this region. The second data set I wanted to showcase is some ALOS pulsar radar imagery. That's what I've just pulled up here. So these are two scenes that were acquired from NASA's Alaska Satellite Facility, both of the same date. In this radar data set is a long wavelength L-band data set. So it's dual band containing HH and HV polarization. So I'm just going to come up to my layer mixing here and showcase the RGB that I have on. So we have an HH, HV, HH RGB for this radar data set. Just so you can see how I'm displaying it. And these radar data sets, like Becky was saying, are quite useful for wetland mapping because of their ability to penetrate the canopies of woody wetlands. And once that signature goes through, it's very sensitive to moisture conditions and underlying hydrology. And we know that through literature, for example, it does indicate that when available, the combination of both optical and radar data does outperform any in isolation, which is why we try to include it where we can for our various projects. So pre-processing of this radar data kind of include your common radar pre-processing, so resampling, registration with the Sentinel-2 data, and speckle filtering to remove noise. And it is just important to note that this data, it's already terrain and radiometrically calibrated from the Alaska Satellite Facility, and that just really helps us out with the acquisition and preparation of our data sets. And the third data set I want to go over is a digital elevation model from the Arctic DEM. And I'm going to turn that on here through my layer mixing, turn off my radar, and turn on my digital elevation model. So this is a digital surface model, so a DSM, of the Arctic, and it's produced by the National Science Foundation, NSF, and the National Geospatial Intelligence Agency, so NGA. And like I said, it's a DSM. However, it is preferable in our work if we did have a DEM, where the above surface objects are removed, such as a LiDAR product. However, this is essentially the best available data set that we can get working in such remote regions, such as northern boreal forests. So the data set itself was produced using photogrammetric techniques with optical stereo imagery, which was collected from high-resolution digital globe satellites, which is why it's a DSM and not a DEM, because the optical data cannot essentially penetrate canopies and other above-surface objects. But you can see the data set here, and the product I use is a 10-meter product in order to match our Sentinel-2 data. And we pre-process the data to develop other topographic products that are quite useful in wetland mapping and detection. I'll show my first one here, which is a topographic position index indice. And so this measures essentially the local relief relative to elevation differences in neighboring pixels. So what you're seeing here is higher values essentially correlating quite strongly to uplands and vice versa for low values and waterlogged areas or wetlands. The second I want to showcase is a topographic wetness index. So this is an indice that takes into account flow accumulation and the slope of a pixel. So it's kind of indicating the tendency of a pixel to be saturated. So you see high values more likely to be wet and lower to not be wet. So in addition to these two useful indices, I did process a slope raster from this and an aspect you can see here. So yeah, that is our digital elevation model. And one last piece I want to show with our Earth observation data is a false color composite that Becky was talking about previously. So that is our near infrared, shortwave infrared, and red bands from our Sentinel data set. This is really because these bands are best for distinguishing these various wetland types seen in the boreal. And it really helps our analysts select additional model training sites across our project regions through image interpretation. So as I pan up and down here, whereas you see everything kind of looks basically green in our true color imagery at the top, we can now really see quite a differentiation with our false color imagery in the bottom. So I'm just going to quickly change this. So we have this for the next part of the demonstration. Okay. So now I want to get into our kind of a generalized workflow that I've put together for today's demonstration. So we have step-by-step examples and algorithm selections for developing a wetland classification in this boreal study site. So the first we have here is our segmentation processes up in our process tree here. So in general, like Becky had gone over earlier, object-based image analysis works really well for wetland inventories because in the boreal, these systems are complex and extensive, and they really vary greatly with these gradual transitions from one type to another. And I like to say that it's often much different than mapping building blocks, for example, which have a clear end and start position. So our goal here with our segmentation process is to create objects as large as possible. So we're reducing that noise and speckle in the data, but as small as necessary to capture fine or linear features on the landscape. So for the demonstration today, we are going to use the multi-resolution segmentation algorithm that I'm highlighting here to develop a 100 scale segmentation. And for our image layer inputs, we're going to utilize the near infrared, red, and shortwave infrared bands. And then for this, we don't include any radar data because it's far too speckled, or DM data just isn't enough class differentiation within the data in the data set in the segmentation process, but we do use it later for classification. So this is our 100 scale output segmentation. And we are going to, because like I said, it is a multi-segmentation demonstration, we're going to essentially rerun that entire algorithm again, multi-resolution segmentation, but at a 50 scale this time, using the same image layer parameters. So the reason we use multiple scales is because some wetlands are larger complexes and they're more easily identifiable, kind of your open water and your fen and your bogs, whereas other classes such as swamps are really, like we said earlier, more linear and transitional. So we would use the smaller 50 scale to identify them. So I've already run these segmentations just because it would take quite a bit of time, considering the working demonstration that I have here is about 1.5 million acres of 10.5 meter or 10 meter, resolution data. So what I'm going to do quickly is just toggle on the segmentation so you can see what a 100 scale looks like and a 50, in this environment. And you can see the top was 100 and your bottom is your 50. So you can see the more detail that's being captured in that 50 segmentation layer that we'll use to capture our swamps later in the demonstration. So the next step that I want to go over, which is really important, is the incorporation of our field data into our project workflow. So collecting and utilizing field data is incredibly important for our work. Really, the truth data is what provides both our calibration and our validation of our wetland inventories. And it's key for us in running especially supervised machine learning classifications and even editing for any known errors during our post-production processes. So with that, I'm going to go into the setup that I have here. And I have this workflow here of bringing in outside vector data as field data. So the first algorithm I'm going to use here as I open this up is my assign class by thematic layer algorithm, where we take vector polygons of field information and assign the class to the underlying objects. So before I do that, I'm just going to showcase, one second here. I'm going to go to my view, vector layer mixing, and showcase the training samples that I have identified here, and those are the pink boundaries. You can see it's quite a large data set across this project region. So you can see those boundaries. In this workflow that I've developed here, we are then going to turn those classified image objects into training samples. So they'll go directly as calibration. And then lastly, I'm just going to remove any of the classified objects to clean it up. So we'll run these three algorithms right now. And again, it's bringing in the vector information that was field collected and photo interpreted, assigning it to their classes based on the class hierarchy, and then lastly cleaning up the data. So we're essentially just left with calibration sites. So I'm going to turn off the training site boundaries from the vector information, go to my view samples, and you'll see that we have assigned sample classes across the entire study area. So now that we have field data in, the next step I want to do is to perform any masking of any non-wetland or upland classes. So we'll jump into my workflow here for masking. And the first of which would be to mask out the edges of the project. So I'll come over here, which really just contain no data pixels. So for this, use a simple assign class algorithm that uses the brightness layer to identify cells with no data in them and just assigns them to my no data class. So essentially anything that has less than or equal to 0 brightness, we're just going to assign it to our project border. And I actually already ran that because it takes a little bit of time to process. So now you can see we just have a project border. So pretty simple for the first one. The second land cover that we'd like to mask out is anthropogenic regions. So really masking these areas out prior to running a supervised classification, it reduces a lot of the errors in omission and commission due to the bright reflectance of human impacted landscapes in the Boreal. So I'm just going to quickly toggle on and off a vector data set of, as you can see, anthropogenic impacts on the landscape. And so I have an algorithm here for this that's going to assign class by our thematic layer and turn those underlying objects into our anthropogenic class. So I'm gonna let that run. That might just take a second. But as you can see here, as I'm letting it run, you can see that the bright features of this airport look quite similar actually to these bright fen features. So we just wanna isolate those so that they're not mixed up in the process. Open that up, and now you can see you have a nice anthropogenic footprint layer. So our third class, land cover that we want to mask out now is water. And this is mostly done doing a thresholding approach, although I will show you how this doesn't always work perfectly or capture everything we want in the Boreal. So first off, I'm going to go over to my feature view and open up my customized feature here. And what we typically use is a modified normalized difference water index, or MNDWI, which I created over here as a customized arithmetic feature. And this is an indice that enhances open water features. So values ranging from -1 to 1, and high values typically correlating to water features. So I will quickly show you what that looks like across the landscape. So you can see your bright water bodies being identified brightly. However, as you'll see with me in kind of interactively moving across this landscape, you'll see that open water features, especially in the Boreal, they're just quite diverse. They have varying depths. So you can see dark bodies here and more blue bodies here. Some have a lot of overlying aquatic vegetation, such as this pink water body here. And even murky bottoms with kind of varying levels of suspended sediment. And this kind of just leads to varying spectral signatures. So you'll see why using just an indice doesn't completely capture all the water bodies we want. But regardless, I've set up this predetermined algorithm here based on MNDWI, and we're going to assign any of our unclassified objects with greater than -0.3 as open water. So this should capture most of our larger water bodies once the output is complete, but it doesn't capture everything. And what we're trying to avoid here is areas of commission where you're mapping land cover bodies that aren't actually water. So we kind of underclassify and then use supervised classification after to capture the remaining water bodies. So you can see with the blue here, we've captured, like I said, most of the larger water bodies, but there are still some that we'll capture later with supervised techniques. So our fourth class here is our burn data sets. So wildfires across the Boreal are very natural, frequent, and extensive, but they interfere with our classification processes. So I do have a workflow here that I developed, which requires me to have a boundary to isolate a thresholding process. So I'm just gonna pan over to one of these big burns here, which is this green outline on the landscape. And I'm gonna toggle on this government developed burn data set. So I'll make that a red boundary. You can see there, so that's a vector data set. So this boundary is gonna help me, again, isolate the thresholding process in order to identify those burns. And the first part we have here is a 3 algorithm step. We're going to assign class by thematic layer to assign the polygon's burn information into the landscape as a processing mask. So let's do that. That might just take a second. So essentially with this vector polygon, I'm going to create kind of a messy processing mask, and I assign it to this, this general class that's kind of for my own descriptions of the landscape of my class is the to process. And then with this kind of messy mask here, I'm going to use another indices, the normalized burn ratio. And I have a preset algorithm, so anything less than 0.08, we're going to assign as a burn. We're going to let that run. That should be fairly quick. And then any of the remaining objects that weren't classified, we're just going to remove. And you can see that we have a nice burn mask on the landscape so that that doesn't get mixed up in our classification process later. Okay, so now that we've done as much masking as we can across this landscape, the next piece that we want to do is a supervised classification of our study area. So what we're going to do is we're going to run this on our unclassified objects at the larger 100 scale. And what we're going to do, I have this set up here in my process tree. We have field data brought in already. I'm going to open this up. Is we are going to use the classifier algorithm and use the random trees type. So this follows Breeman's theory of essentially random forest classification. And we use this because it can handle high data dimensionality, multiclinarity, so a lot of data sets essentially, which is what we're working with here. As I open up my feature inputs, you can see all the indices and radar, DM, and optical data we have incorporated here. So really the parameter that we work with most is the tree growth parameter. Essentially, literature indicates that a high value is thought to lead to a more consistent variable importance. So that's our training random trees, and then I'm going to apply that, of course, across our unclassified objects in the 100 scale. I'm just going to let that quickly run. This is the longest part of my demonstration. I did want to do a live classification, so that should take about a minute or so. But in the meantime, just to kind of describe what it's doing, again, it's a random forest classification across our unclassified objects, and the training data set we used here, if you follow me into my class hierarchy, included our upland classes, and then bog, fen, and open water classes. But we did omit swamps because, like I said earlier, we want to transfer that information from the 100 scale to the 50, and then identify swamps at that finer segmentation scale. Because again, they're more transitional and linear and quite difficult to map. So this first classification is just our easier, larger complexes. And this is something quite handy with eCognition, is you can transfer your information from high to low or vice versa, and you can capture what your various land covers are with the software. So this should be done in a second, which regardless is still very impressive, considering if you look at my project workflow in the bottom right, we're mapping almost close to 150,000 objects, all with unique information and quite a depth of Earth observation data. Actually, while we're waiting here, just another fantastic piece of eCognition is, at least with these projects and what we're doing, because we have such a depth of classes, especially in, for example, in this class hierarchy, is that once you have a classification, you can roll these different classes up into their larger hierarchy. So if we wanted to, once the inventory is complete, see something binary such as upland versus wetland, we could easily roll that up and kind of see that general classification across the landscape. Or for example, in this process that I have here, I did forget to mention that my field sites have separated out different fen classes, and that's just because their spectral characteristics across the landscape are very diverse. So for my visual demonstration, I've just rolled it up into one general fen class, but as I hover my mouse over the landscape, you can see, for example, as I zoom in here, various different fen types, even though that's all one general class. But anyways, now we have a classification across our landscape. this was random trees, supervised classification. As I was saying, you could roll the various fen classes up and down, or the uplands into a generalized class. But yeah, this is our first cut at a classification. And so I'm going to running out of time here, so I'm going to roll over this kind of quickly. But what you can do with supervised classification is after you run the process, there is a really handy algorithm in here using the query function, and you could output an importance table for how important each variable was in your classification process. So I've already run that, and I'm going to quickly go over to this Excel spreadsheet that it pops out. And you can see based on rankings which classes are most important. And typically with wetland mapping, we see optical data sets most important. So something to analyze your data with later. So our fifth step, now that we have this, is to use that finer scale segmentation, so the 50 layer, to identify swamps, which are kind of, for the most part, lumped into this green fen classification that I have. So for this, we're going to run a binary supervised classification of fen versus swamp, and we're going to isolate it by this fen classification. So what we need to do first is we need additional field sites at our 50 scale. So I'm just going to go and quickly clean up my previous samples and delete them. And similar to what we did before, we use a assign class by thematic layer, image objects as samples, and then clean up the data. So I'm just gonna let these quickly run as it just take a second. And this thematic vector data set I have is contains fen and swamp calibration samples again. So we're just gonna classify fen versus swamp at this lower level to identify those features. So run that, run that. And if I pan over to my view samples, you'll see I have more samples across this landscape. So what we want to do at the 50 scale is we want to create a mask which corresponds to the fen classification. So what we're going to do is we're going to pull it down using an assign by super object algorithm. And you can see we're just going to classify this yellow 2 process mask using random forest again, but this time on just fen and swamp. And that should identify our more difficult swamp class. And this one should run a little bit faster than our 100 scale because we're mapping less objects this time. So there you go. We've identified the teal green swamp, or excuse me, the teal swamp out of our fen. You can see it's these darker signatures here. And now our final step would be an accuracy assessment. So what I'm going to do is I'm going to pull down the information at the 100 level to our finer scale segmentation where we have no information. And I've already set this up, so it's a assign class by super objects algorithms. And from here, we can do an accuracy assessment, but first we have to run or use more thematic training data. So just going to delete my old data. And we're going to go to this testing segmentation layer, which is just a copy of our 50 level. And similar before, we have a vector data set, which has testing or validation data set in there. So unclassified by thematic layer. And then we're going to turn that information into samples. Take 1 second here, clean it up. And at this level, you'll see we've got training data set, or samples, excuse me, across our project. So let's bring down all that data. And we have our classification here. We have samples, and we're going to go to the tools, accuracy assessment. at the testing level, and we're going to change the statistic type to error matrix based on samples. Once we run our show statistics, we get these error matrices, which are really useful for kind of running an iterative process of wetland mapping. So we'll set up these workflows and classify the landscape, run an error matrix, and we'll be able to see which classes perform well and which ones didn't as much. And we'd focus our manual editing and photo interpretation on those classes, for example. Yeah, but that's I'm kind of running out of time here, but that's essentially our workflow for identifying wetlands across the Boreal. As you can see, again, we could roll up our data and see how much wetland, gray versus green here. So the green is the wetland extent. You can see how much wetland is really prevalent across these Boreal forest regions. But with that is my workflow. Sorry, I had to go a little bit quicker at the end here. But in the meantime, I think we're gonna do questions first, and then before we end, we might have a time for just a couple here before I pass it back off to our council organizer.
Great, Michael. So we do have a question that came in that says, where can I find DUC wetland mapping online GIS map? So if,
yeah, do you want to do that? Or I can answer that.
Oh, go ahead.
Yeah, sure. So we have the live viewer, like Becky showcased, which is the Canadian Wetland Inventory interactive map. And then for live GIS data, it's usually through a request. Although there is the 5 major wetland classification in Alberta, for example, available through Government of Alberta distribution sites. But otherwise, you can send a request through DUC on our website, and those requests will come to us, and we will work with you.
Nice. Okay, next question is, what is your rationale to include aspect into wetland classification?
Sure, I can do that if you want as well.
Yeah, I'm not sure, so you go ahead.
Sure. Yeah, absolutely. Well, actually, we have a great example of some previous work. So the field campaign that Becky was talking about earlier in Yukon, Dawson, and various wetland types such as bogs were actually forming on north slope patterns. So based on that aspect and where they're located, based on those parameters, you can start seeing the formation of different wetland types depending on that. So it's typically not a high driver and classification determinacy, but it is a variable that does help out. So it's kind of on the lower end, but we do include it because depending on region, that aspect might be helping the formation of type, wetland type in its environment.
Mm-hmm. And the next one is, how many training samples per class do you use over this much area? And how many do you keep for accuracy assessment?
Sure. Yep. Well, the first part of the question is a little bit difficult because we're operational based. So really, site selection is often very dependent on budget and time. We'll always say the more the merrier, better for calibration. But I can kind of give you an exact number for the second part of the question, which is we typically split our data 2/3, 1/3. We'll use 2/3 for calibration and 1 for validation. And that's kind of your typical split. But we'll try to include at least 15 samples of a class for us to provide validation. Sometimes it's very difficult to collect the minimum number we need across a project region, just because the prevalence of a class just isn't there. So trying to balance the science-based aspects, but also the operational aspects of the work that we do.
Mm-hmm. I think I can answer a couple more questions here. So
Sure.
Are SAR and multispectral data available online? And yes, they are. So the SAR we've used, ALOS PALSAR. You can just Google that and it should bring you to where you can download the data. And for multispectral Landsat, you can go to USGS and request data from them there. And again, it's freely available. As well as Sentinel, you can go to the Sentinel Hub. Again, just Google that data. You'll be able to download data from there as well. And what software are we using? So Michael was presenting on the eCognition software, and honestly, that's where we spend 90% of our time. Other stuff we use, for example, to perform mosaicing is on ArcGIS. Which is more reasonable, PCI geomatics or eCognition?
Do you want me
Great
to do that
question.
one?
Yeah, I mean, I've only used PCI a handful of times, so I'm not really sure. So if you've used it more.
Yeah, well, I think the contrasting aspect here is PCI has recently included object-based image analysis. And so we've actually given that a try, and it's great, but it's not as multifunctional as eCognition. It by far is the best platform for us in using multi-segmentation scales, interactive manual editing, and photo interpretation. It is the best for our purposes, where unfortunately our workflows aren't always completely standardized. There's a lot of interpretation involved, and eCognition really provides us that avenue for doing those aspects of wetland mapping.
Awesome. And I'm not sure if we should answer any more questions or not.
I think based on time, we should hand it back to our organizers. Okay. So I'm going to, yeah, I'm sure there's probably a lot of really good questions, but
yeah, there seems to be.
Yeah. Okay, I'm just looking for the. Okay, I'm gonna hand that off.
Okay, can you guys see my screen?
Yeah.
Yes, we can. Yep.
Perfect. Yeah, so unfortunately, we don't have time for any more questions. But if you want them answered, we will have a copy of them after the presentation, and we'll be able to forward them to both Rebecca and Michael, as well as our reps here at CANSOL if you want them answered. Or again, feel free to email them for any of your questions directly. So once again, thank you, Rebecca and Michael, for sharing your experiences and expertise on eCognition software and wetland mapping. It was very informative, and we really appreciate you guys taking the time out to be here, and as well to the attendees who took the time out of their day. I know we did go a little bit over time, but I'm glad that we have people that are very interested in the topic as well. So before I conclude, I just want to bring to your attention that we will be holding a training session for Trimble eCognition if anybody is interested. So that will be December 3rd to 5th, basically the first week of December, with special guest trainer Matthias Stangel, who is actually a Trimble technical support engineer coming all the way from Germany. So this training is limited seating only. We don't have unlimited, so be sure to sign up before that's out. And it's a very rare opportunity to learn about eCognition from an experienced specialist. Registration is available on Eventbrite. And for any other questions or concerns, not only on the training or MGIS that you want to bring to CANSOL's attention, you can email Brock Kingston, who is the Senior Account Manager of MGIS here. His email is listed below. It's brockkingston@cansol.ca. So again, thank you everybody for joining us. That's all I have, and that concludes our webinar.